Stars evolve. How do we know this, given this takes place on cosmic timescales far longer than a human life scale? Imagine you are a smart ant, denizen of a forest containing huge trees. The ant lifetime is so short, you'd never get to see birth and death in the forest of the vegetation. What you would see around you are some young saplings, perhaps seeds just sprouting out of the ground. You'd saw middle-sized trees, and you'd see huge trees that form the canopy of the forest. You also might see places where the trees were horizontal and were seeming to decay into soil. In other words, in your snapshot view, with a short lifetime of an ant, you'd see all the stages of evolution of a tree, from seed to sapling to full-grown tree to dead trunk decaying back into the soil, a full cycle of evolution. Astronomers are in the same situation. We live short times, but by deducing how stars work, we can deduce how one form turns into another and what the full cycle of their story is, even though we will not live to witness all of it. And indeed, in space, we see stars at all stages of their evolution, the rare stages of birth and death, and the more frequent and abundant stages of midlife. By looking at these different stages and having a theory of how stars works, we can piece together the entire story of stellar evolution. The fundamental organizing diagram for stars is called the HR diagram, named after Hertzsprung and Russell. This was a tool from the 1930s when astronomers first developed the ideas of how stars worked and how stars evolve. It connects two properties that are fundamental observables of a star: the luminosity, which requires us knowing the star's distance as well as its apparent brightness, and the temperature, by which we mean the photospheric temperature, or the temperature of the visible surface. Note that mass is not plotted in this diagram. It's truly the fundamental driving attribute of a star, but it's harder to measure, so astronomers stick to the things they can measure most easily for the largest number of stars: luminosity and temperature. If we knew nothing about stars, and we gathered these pairs of measurements for hundreds or thousands of stars in the sky, what might we expect? With no theory of how stars work or how they evolve, we could imagine points being scattered in this diagram, any luminosity combining with any surface temperature. But that's not what they saw back in the 1930s. They saw, looking in the solar neighborhood, that stars tended to form a diagonal track in this diagram, ranging from high luminosity and high surface temperature down to low luminosity and low surface temperature. They called this the main sequence. It seemed to be where most stars dwelt in terms of those properties. But also, 50 or 60 years ago, astronomers realized there were stars not on the main sequence with other properties. There were some stars that were much dimmer and yet also quite hot, and these were assumed or calculated to have small radii. These are the white dwarfs. And high up in the Hertzsprung-Russell diagram, there are populations of stars that are exceptionally luminous, and they may be blue or red. These are the red giants, the red supergiants, and the blue supergiants. Stars doing something different than converting hydrogen into helium, and they're physically large. The other thing that was realized decades ago is that if we sampled a typical volume of space, we'd find that the low-mass stars are by far the most abundant on the main sequence, and the high-mass stars are by far the rarest. In fact, the Sun is not even typical in this category, because there are many more red dwarfs than there are solar stars, and there are many more solar-type stars than there are blue giant main sequence stars. This is called the mass function of stars, and it's an important idea about how stars form, because whatever process forms stars produces a power law distribution with many more low-mass stars than high-mass stars. It's interesting that this took a while to realize, because if we just look into the sky at the brightest stars, the stars you might see with your naked eye on a dark night, you see most of the stars are actually giants or massive stars. And that's because we can see those to much further distances and therefore larger volumes than the dwarf stars. Only when we have the power of looking deeply through space for the dimmest, feeblest objects can we properly do the census of what exists in any volume of space. And when we do that, we realize that the brightest stars hugely overrepresent giants and hot stars compared to their true distribution in space. We now can do the true distribution of nearby stars, and we do know that most stars are red dwarfs. Although it wasn't understood immediately, the HR diagram did show the bounds on stellar mass. This is a correlation between two variables, luminosity and surface temperature, where the underlying variable is mass. So the part of the main sequence where the stars are very luminous and hot is the high mass end, and the part of the main sequence where the stars are dim and cool is the low mass end. Spectroscopy was a fundamental tool by which astronomers first classified stars, starting early in the 20th century, and particularly in the middle part of the 20th century. To categorize them by their spectra, you're looking primarily at cool absorption lines imprinted in the outer envelopes of the stars. Remember, the hot cores where fusion is taking place at a temperature of millions of kelvins are invisible because the stars are opaque. So we have to diagnose what's going on within the star from what we can see, the visible light from its surface regions. For purely historical reasons, astronomers classified stars according to their temperatures and produced a spectral sequence running alphabetically, but not alphabetically because of some shuffling of the order from its first version, as O, B, A, F, G, K, and M. More recently, in the last few decades, even cooler stars were added to this sequence, representing the reddest dwarfs. As we move down the stellar sequence, you see different materials or elements appearing in absorption in the outer envelope of the star. The coolest stars, like M dwarfs, actually have molecules like titanium oxide in their spectra. When a star finishes its life on the main sequence, it's exhausted its hydrogen fuel. With no support from the pressure of nuclear reactions, it must collapse and reach a new configuration. So as a star dies, in that sense, it moves off the main sequence, which means its properties change. This, conversely, turns the main sequence into a very powerful tool for applying an age to a cluster of stars that all formed at the same time. As that cluster evolves, the most massive stars with the shortest lifetimes die first, and the main sequence gets truncated or eaten away, starting from the luminous blue end towards the less luminous red end. This animation shows that effect in terms of the time or age of the main sequence stars. Therefore, we can look at a star cluster, measure the HR diagram, or those pair of properties, luminosity and temperature, and deduce the age of that star cluster. This is the routine work that occurs in the Milky Way galaxy to put ages to globular clusters and younger star clusters where stars are forming currently. I gave the general argument in terms of the size of the so-called fuel tank of hydrogen of how long a star should last on the main sequence. Doing the calculation a little more accurately produces a clear and clean relationship between main sequence lifetime and mass. And it goes as a steep power of the mass, the 2.5 power. That's why the lowest mass stars live enormously longer than the highest mass stars. Even though we never get to observe an individual star being born, living its life, and dying, we can piece together the story of evolution statistically. Knowing how stars work and observing their properties through the HR diagram, the combination of luminosity and surface temperature, we can deduce the story of stars. The highest mass stars live short lives, die quickly, and they're the least abundant type of stars, where the lowest mass stars live enormously long lifetimes and are the most abundant stars.